All right, so we've investigated what torque is. We've investigated what moments of inertia are. We've investigated what angular acceleration is. That's almost where we started the whole thing. Now I think we're ready to put all this together and form Newton's second law in rotational form. The sum of the torques is equal to I alpha. Just as a reminder, what Newton's second equation looks like in linear form. Sum of the forces is equal to ma. I've shown the full vector nature here. We talked about the vector nature of the torque. We hadn't actually talked about the vector nature of the angular acceleration. But of course, if torque is a vector, for this equation to be valid, angular acceleration has to be a vector. We can understand that the same way we understood the torques. If this is accelerating angularly, it is doing so about a specific point about which the torques are acting as well. And so because we thought about the torque vector as pointing along the axis of rotation, or at least impending rotation, we can think about the angular acceleration pointing along the same axis. We're going to follow the same conventions. A positive pointing along the positive z-axis means it's positive. Means the torque is positive, and also the angular acceleration. That will result in counterclockwise. That will be a counterclockwise acceleration. I should say that. And negative would be negative z-axis and producing a clockwise rotation, or at least the potential for a clockwise rotation. So this is Newton's law in rotational form. I should point out that we're going to see both of these expressions are valid in the same systems. We're going to see systems now where we have to analyze them linearly and rotationally. So again, the same forces that are over here in this version of Newton's law that we know and love, the same forces that are producing linear accelerations in the x and y directions, and maybe z, are causing torques over here. And so if I need to analyze a system, I now just have a way to get more information. In a two-dimensional system, I was able to get two equations out of this. We're going to keep the torque to one dimension, but that means I can get another equation out of this one. So I can get 2 plus 1 is 3. If I have a three-dimensional system over here, I can get 4. But it's important to remember that both of these tools are at your disposal if you're doing Newton's second law problems, because in general, we expect translation and rotation out of all systems. Later on, when you go to more advanced mechanics courses or engineering dynamics courses, you're going to calculate the torques around each axis. And so you'll have 3 equations that can be generated from here as well, giving you a total of 6 equations if you're in a full 3-dimensional treatment. You get 3 from linear world, 3 from rotational world, enabling you to solve for up to 6 unknowns. So that is Newton's second law in rotational form. It's very similar to Newton's second law in linear form. What do we do with it? Well, if we need to know what sort of acceleration is being produced by a net torque, we just go here. If I need to know if I can use angular kinematics, which means my angular acceleration has to be constant, this is a good way to analyze the system and see if my angular acceleration is constant. All this to say, I'm going to do the same stuff with this that I did with my linear form. It's just slightly more complicated because I've got things buried inside these terms. But the math is really not more complicated as long as I know how to unpack. And so when I draw free body diagrams now, I'm going to relax the restriction that it's a point with just forces and angles. Now, you will find some professors that don't like calling what we're going to do here free body diagrams, but that works fine for me. We now have to draw the extended object and show how the forces are acting on it, both their directions, angles, and points of application.